In this lesson, we'll be covering quite possibly the most intimidating, I'll say, topic on the quantitative reasoning section of the GMAT Focus Edition, which is basic quadratics. And I can't stress this enough. The quadratics that you're going to encounter here are relatively basic. So let's start by just defining what a quadratic is. It's something that can be represented as a parabola, and it's a function, on the coordinate plane. Now, again, there is no geometry on the GMAT focus, but this is to say that there are more than one value that can satisfy the formula or the function. So you could have possibly multiple values satisfying the equation at one time, which is like a square root of 64 could be 8 or positive 8 or negative 8. Your root or solution is a value for x that satisfies all parameters of the quadratic equation. Your binomial are the two values separated by plus or minus in parentheses, often known as a quantity. And your standard form of a quadratic is going to be ax squared plus bx plus c when a, b, and c are constants. And in terms of the a and the b, these are your coefficients of x squared as a degree and x as a term. These are most reasonably going to be solved by setting your quadratic equation equal to 0 and doing what is known as factoring. So strategically, the quadratic equation, you will note, is not part of this lesson, and you can certainly go look it up. It's fine, but it's not necessary for any GMAT quadratic based problem solving question. So don't feel like you need it, and I really will say that it's probably more time consuming than what the exam expects you to do. Instead, you want to seek simple methods of factoring or distributing to solve GMAT quadratics. And do remember that you may have negative roots for these solutions. And you can also consider our alternative tactics to maximize efficiency, meaning modeling, back solving, logical evaluation, and estimation. Because if you determine that the structure of the binomials is such that x has to be a negative and a multiple of 6, well, if only negative 12 is there that satisfies those two conditions, you can solve for the correct answer immediately and not have to do the extra steps. These quadratic based questions, especially when you start to see degrees in like the thirds or fourth degree, they're what I like to call engineer breakers, because if you try to do it the technical approach, you can, but it's really going to be time consuming no matter what you do, since you don't have a calculator in the quantitative reasoning section of the GMAT focus. So first, we're going to talk about how you distribute binomial quantities through multiplication. So you may recognize the acronym FOIL, and that stands for first, outside, inside, last. Once you FOIL, you then combine your like terms with the same variable and same degree or exponent. So let's take a look at the example of distributing the binomial terms, or binomial quantities, 3x plus 7 and 2x minus 4. So first, we multiply the 3x times the 2x, we get 6x squared. Then we multiply our outside terms, the O in FOIL, and we get 3x times minus 4, which is negative 12x. Then we multiply our inside terms, so that's a positive 7 times a positive 2x for 14x. Then we multiply the last terms for the L in FOIL and get 7 times negative 4, which gives us negative 28. We combine the like terms of negative 12x and 14x to get 2x, and we find that 3x plus 7, the quantity, times the quantities 2x minus 4, is equal to 6x squared plus 2x minus 28 once you complete your distribution. Now, to solve standard form quadratics, you're going to have to do what is known as factoring. First, you have to set the equation equal to 0. That is just the way that it works, and you're going to remove factors common to all of the terms, basically by dividing them out. Then you're going to want to write parentheses for your binomial pairs, placing the terms producing the ax square on the left side of each of the binomial parentheses. Then you're going to consider the operands, meaning plus or minus, in those binomials based on the signs in the quadratic. And then you'll place the terms producing your c term, the constant, and summing to the b term, the coefficient, on the right-hand side of the binomial parentheses. So let's take a look at the example of 6x squared plus 2x equals 28. So in order to solve this, we first have to subtract 28 from each side to set the equation equal to 0. So we find that 6x squared plus 2x minus 28 is equal to 0. Then we see that there's a 2 for each of the terms. So we've got 6x, so 6x squared, so we can pull a 2 out of 6. We can pull out a 2 out of 2x, and we can pull a 2 out of 28. So we've got 2 times the quantity 3x squared plus x minus 14. Now we're going to need to factor the simplified quadratic of 3x squared plus x minus 14. So we're going to write the binomial pairs for the ax squared term, which in this case is 3x squared. And the only way you'll get to 3x squared reasonably is going to be 3x times x, because 3x times x, 3x squared. Then we need to consider the pluses and minuses in our quadratic that are required to produce our constant term, in this case, negative 14, because it's less than 0. So if we had an x coefficient that was positive and a constant, a c term that was positive, we'd have two pluses in our binomials, but we don't, so that's not what we're going to have here. If you had an x term coefficient that was negative, but a c constant that was positive, that would mean you'd have to have a minus and a minus. But again, our constant is not positive, so this is not what we're going to have in this instance. But anytime your constant term, your number without a variable, is less than 0, you must have a positive and a negative in some order within your quantities, your binomials, that is. So in this case, it's going to be 3x plus and x minus, because we know that we're going to end up with a minus x. And we'll see in a moment how that works out. So we've got our binomials and our quadratic factored out so far as 2 times the quantity 3x plus something, and then the quantity x minus something equals 0. So we need to consider the factors of negative 14 that will sum to 1 with that 3x coefficient. So if we had negative 2 times 7, that would equal negative 14. And if we have negative 2 times 3, that's negative 6. And if we had positive 7 times 1, that gives us 7. And minus 6 plus 7 gives us the exactly 1x that we seek. So we know that our proper factoring is going to be 3x plus 7 and x minus 2. Then we solve by finding the values that will produce 0, because we've got a bunch of multiplication and it has to produce 0. So within the binomial, we need to find a value of x that when multiplied by 3 and added to 7 results in 0, and a value of x that when you subtract 2 from it produces 0. So we know that when 2 minus 2 occurs, it becomes 0. So x could equal positive 2, or it could equal negative 7/3. Because if we put negative 7/3 next to the 3 in the first binomial, well, then we divide by 3, because you take the 3 and cancel the 3, and you have negative 7 plus 7, which of course produces 0 as well. And that's a relatively complex quadratic. You're probably not going to see something that detailed and that convoluted on the exam with the coefficient in front of the x squared term, but it's possible, so that's why we have this example for you to work through. Now, the more likely thing you'll encounter on the exam are what are known as the common quadratic identities. So these are structures of quadratics that have known factors that you'll probably want to commit to memory. So if you see a quadratic in the form of x squared plus 2xy plus y squared, that is just the binomial x plus y squared. Because if you expanded that, you'd have x times x, x squared, x times y, 1xy, x times y, another xy, so 2xy's, and then y times y is y squared. Then if you see a quadratic in the form of x squared minus 2xy plus y squared, well, that's going to be the binomial x minus y times itself or squared, because x times x, x squared, x times minus y, minus xy, x times minus y, minus xy, so 2 minus xy's, and then minus y times minus y, the minuses cancel out, and we end up with a positive y squared. And the last one is what is known as the difference of squares, and that's x squared minus y squared is going to be equal to the quantity x plus y times the quantity x minus y. So the reason for that is because if you FOILed out the x plus y and the x minus y, you'd have x times x squared, x times minus y minus xy, x times y positive xy minus xy plus xy cancel out to 0, and then you have y times minus y for the minus y squared because positive times negative stays negative. Now, strategically here, you will want to memorize these common quadratic identities to expedite quadratic manipulation on the GMAT, and consider these quadratic identities as a possible factorization for any quadratic with a constant c term that is a perfect square. So, like if your constant is 4 or 25, you may say to yourself, hey, is a common quadratic identity viable here? You can also see common quadratic identity factorizations as shortcuts for hard technical arithmetic, algebra, and word problems. And remember that it is possible to combine quadratics as systems of equations as well. So let's go on over to the whiteboard and take a look at how quadratics can present themselves in problem solving questions within the GMAT focus quantitative reasoning section. So here we have a sample problem solving question, A, B, C, D, E. As always, put a little line over top, and we skip to the end. We see that we are being asked for the compound value of x times y. And we've got some real numbers, so I might write them out. We got negative 27, negative 9, negative 3, 9, and 27. And you may be thinking to yourself, well, maybe I could model this with my answer choices because I can see what the outcomes are. But because this is a very technically presented problem and we're being asked for a compound value, it's going to be hard to work that through because I can't just plug in for x or y. I'm going to have to be like, well, could it be negative 3, positive 3? Could it be x that's negative? Could it be y that's negative? All these sorts of things are going to be a little bit more complex. So I really want to try the technical approach. And remember that if the algebra is clearly apparent, really attempt the technical manipulation first. So we see we've got a couple of values. We've got x minus 9. Oops, sorry, x minus y is equal to 9. And we're told that x squared plus y squared is equal to 27. So because this structure is presented to us, we need to recognize that x minus y times x minus y is one of our common quadratic identities. So we can square this x minus y equals 9 by expanding our quadratic and foiling. So we FOIL out, we know we've got x squared minus 2xy plus y squared. And we know that that's equal to 81 because of the given information. Then it becomes a system of equations because we've got x squared plus y squared is equal to 27. So now we can subtract our two equations from each other just as any other system of equations. So we keep our minus 2xy, but our x squareds go away, our y squareds go away. And 81 minus 27, 81 minus 20 is 61, 61 minus 7 is 54. So then we're trying to solve for xy, not the individual values. So we divide by negative 2 to solve for the exactly sought value to see that xy is equal to negative 27. And our answer is A through an entirely technical manipulation by recognizing the common quadratic and applying what we know of systems of equations. So let's scroll on down and take a look at another problem where it's probably a little bit harder to recognize that we're dealing with a possible common quadratic identity. So setting this up, we got A, B, C, D, E, put a little line over top, and we're being asked for the interesting question of, or the interesting value of not a factor of 7 to the 8th minus 5 to the 8th. And we got real numbers, 2, 5, 12, 24, and 74. So, looking at this as a quadratic identity kind of problem, I've got perfect squares. This is actually a difference of squares. Now, the way that we're going to have to factor that out is we're going to have 7 to the 4th plus 5 to the 4th times 7 to the 4th minus 5 to the 4th. Now, knowing what I know of the exam, I'm probably inclined to just say they're not really worrying about this side because that 7 to the 4th plus 5 to the 4th is not a common quadratic. I can't really factor that any further. It's going to be huge. It's not one of my answer choices. So this is kind of logically irrelevant. At least this half. So then we can further factor this other half, though, down as another difference of squares. Because we know that we can rewrite that as 7 squared plus 5 squared times 7 squared minus 5 squared. So now I could see that we're starting to deal with more reasonable um, values, right? Because 7 squared is going to be 49, plus 5 squared is going to be 25. So that is equal to 74. 74 clearly is a factor, so that's out. Then we've got 49 minus 25, which is going to be equal to 24. So 24 is a factor. So D is out. And then I could see that 12 and 2 are also factors of 24. I could further factor 7 squared minus 5 squared as another difference of squares. I'm going to point it out, even though we don't necessarily need to do it. And we learn that it has to be 5. That is not a factor of 7 to the 8th minus 5 to the 8th. So that's how we can find a difference of squares in kind of an interesting place. Now, another thing to note about this problem is because we're looking for what is not a factor, and I'm going to just kind of put this as our logical evaluation alternative elimination. If you're stuck and you don't see how to do the difference of squares, make sure that you eliminate the answer choices that are absolutely impossible, because if it was not a factor, there'd be 2 other things that had to be factors. So I can see A has to go away immediately, because if 2 is not a factor, then 12 is not going to be a factor, and 24 is not going to be a factor, and 74 is not going to be a factor. So I can't have it be 2 or 2 and 12 and 24 and 74 all simultaneously being not factors. So A goes away immediately. Same thing with C. C has to go away immediately too, because if 12 is not a factor, then 24 can't be a factor. And again, I can't select C and D concurrently. Same thing, I can eliminate choice D, 24, as not being a factor. Kind of a double negative there. But that's because if we selected 24, that would mean both 2 and 12 were factors. But if 2 and 12 are both factors, then 24 has to be a factor as well. So we can see that even if you find yourself with a relatively difficult technical manipulation, don't put yourself in the position where you're completely blindly guessing. At least logically evaluate first. See if you can get down to what would really be the only viable options. If you can recognize the redundancy of the choices of either B or E, you're probably more likely to pick E or B anyway, just because you're like 5 is an odd maybe, and that seems reasonable as a reason to eliminate. Anyhow, that is how you can work our basic quadratics, including in some places where you might not have expected to find them. So go ahead and practice some of your own quadratic problem-solving questions to improve at what may be, for many people, a more intimidating aspect of the GMAT focused problem solving quantitative reasoning section.